We are now back and we're wanting to look at problem number 4 on a previous exam, number 3. This is an operational amplifier problem, and we're trying to find this output voltage V0 if it exists. And what we're told is that this particular input voltage is actually a DC value of 2 volts, and we're assuming that the power supply voltages are 15 volts and minus 15 volts. And what we want to check at the very end is if our output for V0 actually ends up exceeding those. Let's say that V0 ends up being 18 volts. We know that can't happen. It cannot exceed these supply voltages, and we would then conclude then that V0 was actually equal to 15 volts, and it would not equal 18. Let's check that though and see if we are in saturation at the very end, or if we're continuing to be in the linear region of operation after analyzing the circuit. Before we start, what we want to do is check on whether or not we have negative feedback, and as we've indicated, it looks like we should, because we have the feedback of our output voltage being fed back to the inverting terminal of our operational amplifier. Indeed, if VD right there is equal to 0, if V sub D is positive, then V0 is going to be a positive number which gets fed back, and through this minus it's going to, remember, V sub D is V sub P minus V sub N. If the output is now coming in here as this A sub OL V sub D, this is now, through that sign, causing V sub D to get smaller, and so we have negative feedback in place. We can now start analyzing our circuit with the assumption that V sub D is equal to 0, which is our summing point constraint, and we always have that the currents going into the op amps are 0. So let's now get started. This now allows us to say that V sub D is equal to 0. Let's look at analyzing this circuit. What we are going to do is try to go from the input to the output. In making that transition, what we want to do is probably do a KVL there. We will probably then do a KCL there. We may then have to write another KVL, maybe around here. And remember this, the difference now that you might want to take note of is that we now don't have that positive or non-inverting node grounded. It's actually raised a little bit, and it's raised to 1 volt with a DC source, so we'll have to account for that when we're doing these KVL loops. We'll then probably do a KCL there, and probably do a KVL around the output loop. Again, here we're starting at ground and we're finishing at ground, and so that is actually a loop, and you could sort of connect it that way if you wanted to. Let's clean this up a little bit and get started by doing our first. So we're going actually from input to output in our thinking or in our processing. Let's do a KVL around the input path. Or we now have minus V sub I, and maybe what we want to do is start drawing some currents so that we can keep track of those. Let's just say, let's label those consistent with our resistors. And it really doesn't matter which direction we assign these currents. Everything should work out And so I'm just going to assign these maybe differently than what's indicated in previous worked solutions, but hopefully you'll be able to follow along. I think I've actually defined I sub 3 differently than in the past, so let me call that an I sub 3 bar, just so that you don't confuse that with I sub 3 in earlier solutions. If I now do KVL around the input, I have minus V sub I going into the negative terminal. With the passive sign convention, I'm now dropping a voltage across that resistor from left to right, and I have R sub 1, I sub 1. With the summing point constraint, this V sub D, I now have minus V sub D. That will go away in our summing point constraint, and if we're out of the linear operating region, or if we've saturated, then we'll have to come back and make some adjustments, but we're going to assume that's equal to 0 plus, and now we're going into the positive terminal of that 1 volt offset in DC voltage before we reach ground. And we know a few things, or we've been given a few pieces of information. We know V sub I. V sub I was 2. R sub 1 is 1,000. I sub 1 we don't yet know. V sub D, by the summing point constraint, is 0. And we have plus 1 is equal to 0. The only unknown in that circuit now, or in that equation, is I sub 1. We can now divide through by that 1,000, and we have 2 minus 1 if we take those constants to the other side, or we now have 1 over 10 to the 3, or 10 to the minus 3, or 1 milliamp for a current I sub 1. We've now found some of the information that we want. We're actually trying to find V naught, and consequently we probably are going to want to find I sub 3 bar and I sub 4 in this last section, or the rightmost section of our circuit, so that we can find this voltage drop V naught. We found I1. I1 now can actually be related to these currents floating around, not floating, but actually existing in these other resistors by doing a KCL at the inverting terminal, and remembering this particular current going into the op amp is equal to 0, meaning KCL at, what do we want to label that? Maybe I could label that point, or that node, 2 for reference purposes. Now I can do KCL at 2, and that says that I sub 1 is equal to I sub 2, and I sub 2 then is 10 to the minus 3 amps, or another 1 milliamp. Let's now look at, we want to find I sub 3, and we don't know I sub 4, so if we started to write a KCL at that particular node, we would have 2 unknowns. If we actually start working our way through this circuit from left to right, we can do it if we write this sort of sequence of KVLs, KCLs, KVL, KCL in the right order. We can only have one unknown in our circuits that we're, or the equations that we're actually ending up with. Let's do a KVL now. Let's call that particular yellow highlighted KVL loop as KVL 3. If we now do KVL around 3, we go into the negative terminal of this DC offset voltage, and we now have minus 1. We then are going to go in the direction of I sub 2 through r sub 2 and in the direction of I sub 3 bar through r sub 3 before we reach where we started, and that's then our KVL equation. We have minus 1 plus v sub d plus r sub 2 I sub 2 plus r sub 3 I sub 3 bar is equal to 0. What we know from the summing point constraint that this is equal to 0, we've already determined what I sub 2 is. Above, that was 10 to the minus 3. R sub 2 and R sub 3 we know, and consequently the only unknown in that expression is I sub 3. Or R sub 3 I sub 3 bar is now equal to 1 minus R sub 2 times 10 to the minus 3. Let's divide by R sub 3, and we now have 1 minus R sub 2 is 2 times 10, or 2,000, and R sub 3 is 1,000. This now allows us to say that I sub 3 bar is, these actually cancel, and we're left with minus 1 over 10 to the 3, or minus 10 to the minus 3, or minus 1 milliamp for what we've labeled as I sub 3 bar. Now that we know I sub 2 and I sub 3, we can go back into our circuit and say, well, I can, if I find KCL at node 4, which is going to say that I sub 2 is going in, I sub 3 bar and I sub 4 are both leaving, I can now solve for I sub 4. KCL at 4, if I remember what I just said, I sub 2 was going in. That needs to sum or equal the currents going out. We know I sub 3 bar, we just computed it. We know I sub 2, and I sub 4 then is I sub 2 minus I sub 3 bar. This was 10 to the minus 3 minus a minus 10 to the minus 3, or I sub 4, hopefully, is now 2 times 10 to the minus 3 amps, or 2 milliamps. That's I sub 4. Let's now go back to our circuit, and we're almost there. We now know all of the currents that we've labeled that really are in existence in this circuit. We want to find V0. Let's now look at, and we can do a KVL whichever way we want. Suppose we start here and go that way with a KVL, and we'll call that at the output. So let's do a KVL at the output. We're going to then go in this direction through R sub 3, but when we go in that direction, we're going opposite to the positive direction that we've indicated for I sub 3 bar, and we'll have to account for that in our sign, meaning the voltage dropped across that resistor is from top to bottom with the passive sign convention for I sub 3 bar. We'll then go this direction, which is consistent with I sub 4 that we've labeled, and consequently that voltage drop will be from left to right, and then we'll come down through V0. Let's now do that for KVL at the output. KVL at the output now says that we have minus R sub 3 I sub 3 bar plus R sub 4 I sub 4 plus V0 is equal to 0. We now can solve for V naught. V naught is R sub 3 I sub 3 bar minus R sub 4 I sub 4. R sub 3 was 1,000. I sub 3 bar was minus 2 milliamps minus R sub 4, which was 2,000, and I sub 4 was 2 milliamps. These powers of 10 basically cancel each other out, and we're left now with those two canceling, and I now have minus 2 minus 2 times 2, or, wait a minute, I sub 3 bar was not 2 milliamp, it was actually 1, so I've made a mistake. Let me correct that. This was actually just minus 1. Let's go back and make sure that's correct. I sub 3 bar was minus 1 milliamp, not minus 2. So now if I make that correction, I end up with a value of minus 1 here, and I have a minus 4 there, or I now have V naught is equal to minus 5 volts. And this is actually less, well, in magnitude, that's bigger than minus 15, and it's less than plus 15, and because of that we are in the linear operating range, and this is now our answer that we can be comfortable with and claim that that's the right answer.